Okay, good afternoon. So yesterday we were in the 16 group elements. So we were seeing regarding the some of the properties, characteristic features of the 16 group, like electron gain enthalpy, electronegativity, ionization energy, atomic and ionic radii. All these we have seen. Let us move further. That is physical properties. Physical properties. So in the physical properties, first one, if you take the existence, in what form are they existing or occurrence? So there, in the existence, what you have is, so oxygen and sulfur, they are non-metals. Oxygen and sulfur, they are non-metals. Further, selenium and tellurium, if you take, these two are metalloids. These are metalloids. Metalloids meaning where they exist as metal also, they show the properties of metals and the non-metals. Polonium, if you take, it is purely a metal and that too radioactive metal. So this is what is the existence. How, in what form are they existing? Radioactive. Radioactive meaning it is giving alpha, beta, gamma rays, etc. Then coming to the allotropic form. Okay. Second one is allotropic form. Allotropic form. What is allotropic form? Allotropic form is same element existing in 2-3 different physical forms, but chemical properties will be the same. Chemical properties is going to be the same. So now for each one, if you take oxygen, oxygen, it is existing in the O2 and O3, two different forms. Both are gases only. Then sulfur, if you take, sulfur is existing in the form of rhombic, then monoclinic, and plastic. Three forms of sulfur are there. These three are the allotropic forms of the sulfur. Then selenium. Okay, selenium, it is existing in the two forms. One is red form. Now this red form is non-metallic. Red form, if you take, it is non-metallic. While if you take the other white-gray form, so that white-gray form is metallic. White-gray form, it's going to be metallic. So again, you can see in the same element existing in two different forms, allotropic forms. One is non-metallic, other is metallic. Their uses may be different. Okay, so when you extract and maybe use it for some purpose, the uses will be definitely different. Then tellurium, if you take, tellurium is existing in two different forms again. One is crystalline form, crystalline and amorphous. Crystalline and amorphous. These two forms. Later, the last one, polonium you take. Polonium, it is existing in alpha and beta forms. It is existing in alpha and beta forms. So these both alpha and beta forms, both forms are going to be metallic. Both are metallic in nature. Both are metallic in nature. Next, coming to the melting point and boiling point. Third point, melting point and boiling point. Melting point and boiling point. So melting point and boiling point increases down the group. Okay, it is increasing down the group. It is increasing down the group. Why does it increase? Van der Waals forces will be stronger between the particle, one particle and the other particle, or between one atom and other atom, the van der Waals forces shall be stronger. Atomic number increases. Okay, because of these both, atomic number is increasing as well. Whatever the van der Waals forces are there, they'll be increasing, and that's going to be a stronger uh, force, and that's why the melting point and boiling point shall be strong. Then in this, one more property is oxygen. If you take oxygen, it is normally existing as a diatomic form. O2 form it is existing generally because it is stable. So when it is existing in the diatomic form, it is stable. Further, sulfur, if you take sulfur, it is existing in the form of polyatomic. It is existing in the form of polyatomic, diatomic and polyatomic. Next. So these are the physical properties of these compounds, these elements. Let's go to the next, chemical properties. Their trends mainly here what we learn is how the trending is there, whether it is increasing, decreasing, all that trend we are going to learn over this topic. Let's see. So next is chemical properties. Chemical properties, first one, oxidation state. In the chemical properties, oxidation state. Okay, so oxidation state. So in the oxidation state, what is there? See, it can be existing, these elements can be existing in -2, +2, +4 and +6. These are the various oxidation states of the oxygen family elements. -2, +2, +4 and +6. Then here in this, if you take oxygen, normally its oxidation state is going to be -2. Its oxidation state is -2. But only in the case of OF2, oxygen difluoride, if you take, a fluorine atom is more electronegative than oxygen. Fluorine is more electronegative than oxygen. In this case, oxygen shall be +2. Oxygen donates 2 electrons there. Then, coming to the other elements, sulfur, selenium, tellurium. Sulfur, selenium and tellurium. These if you take, so they are usually existing in the +4 form. Okay, with oxygen if you take, they are existing with the oxygen, so there it is going to be in the +4 form. But if they are existing with the fluorine, so usually +6 form is more stable than the +4 form when it is existing with the fluorine, when it is bonding with the fluorine. So when these elements are bonding with the oxygen, +4 form, when these elements sulfur, selenium, tellurium is bonding with the fluorine, that time it shall be showing the +6 form. Okay. Then later, polonium, if you take polonium, it is existing in the +2 form and the +4 form. So it is not showing the -2. -2 is shown by all, but polonium, it is not showing the -2 because it's a metal, and those metals, remember, because they are electropositive, they would rather donate the electron. Their tendency is to donate the electron. So when their tendency is to donate the electron, and definitely it's going to be a electropositive metal. Only +2, +4 shall be the oxidation state it is going to show later. Next, if you come down the group, what about the stable oxidation state? So plus 6 oxidation state if you take decreases down the group. Plus 6 oxidation state, plus 6 oxidation state, it is decreases down the group. It is decreases down the group. Why? Plus 4 oxidation state if you take, plus 4 oxidation state. So plus 4 oxidation state is increases down the group. Increases down the group. Why does it increase down the group? Okay, it is because of the inert pair effect. We have learned earlier also. Inert pair effect. Inert pair effect. It is going to come down. So 4 electrons only are going to participate more strongly as you come down the group. The other 2 electrons are not going to participate. So that is what is inert pair effect. So here what happens is, at the same time, one more thing regarding this. Plus 4 and plus 6 oxidation state, whatever is existing, plus 4 and plus 6, these are going to form covalent bonds. Plus 4 and plus 6 oxidation state of these elements, they usually form covalent bonds. Now, what is the reason for this also? Because the electrons will be promoted to the vacant d orbitals. The electrons are going to be promoted to the vacant d orbitals, and down the group, plus 4 oxidation state becomes more still. Electrons donated, promoted rather, not donated, promoted. Electrons are promoted to d orbital. Electrons are promoted to d orbital, and further the next is plus 4 is more stable. Plus 4 oxidation state if you take, it is more stable. See, these whatever the thing is written on the board, using this also you should be able to expand and write in the examination. Regarding this itself, if it is asked, okay, a short note you make out of your own whatever idea. So regarding oxidation state of the oxygen family elements, this much, whatever the words are given you, you should be able to make a short note out of that. What all different oxidation states are there? Normally, oxygen is showing which oxidation state, and exceptional case is this. Then the other ones, they can exhibit plus 4 and plus 6. Minus 2, it is only for oxygen and these elements. Polonium does not exhibit the minus 2, it exhibits plus 2 and plus 4. Then in this plus 6 and plus 4, if you compare those two, so plus 6 if you take, it is decreases down the group as you come down the group. Plus 4 if you take, it is increasing down the group. This is because of the inert pair effect. In the p block elements, especially nitrogen, boron, all these, whatever are there. So 2s2, 3s2, 4s2, like this, the electrons are filled. ns2, np1, ns2, np2, ns2, np3. That ns2, what I am saying, those electrons remain inert. They do not take part in the bonding. So there, the plus 4 oxidation state is going to increase down the group. Further, in this again you have the anomalous nature of oxygen. Okay, and the last part you have to write regarding this, plus 4 and plus 6, they both form the covalent bond. And Y means whatever extra electrons are there, they are promoted to the level. Okay, next. Anomalous behavior of oxygen. Anomalous behavior of oxygen. What is the reason for anomalous behavior of oxygen? One is small size. Because of the small size, oxygen exhibits the anomalous behavior. Second one, it is high electronegativity. High electronegativity compared to the rest of the elements of the group. See, for nitrogen also you have seen this. Okay. Then these two are the main important reasons. Then strong hydrogen bond in water, but is not found in the H2S. That is the reason for this anomalous behavior. 2 points if they ask you. These 2 points you are supposed to write there. It is small in size and it has got high electronegativity compared to the rest of the elements. Further, covalency equilibrium. Covalency. The capacity, okay, the capacity or the tendency to form the covalent bond. How many covalent bonds it can be forming? Usually it is two. Okay, two covalent bonds it is forming. At the maximum, okay, maximum covalent bonds it can be four. Maximum it can be four, but those are exceptional cases, not in all the cases. Exceptional some cases. Because why this is so is because of absence of d orbital. Okay, absence of d orbital. So in the oxygen there are no d orbitals existing. Because of that, the +4 oxidation state or the 4 covalency what it should be showing, it is not going to be showing there. Other elements of the group, if you take the covalency of the other elements, sulfur, selenium, tellurium, polonium, they all exhibit even the 4 as the covalency. Next. Reactivity with hydrogen. Reactivity with hydrogen. How do they react? What do they form? They form the hydrides. Okay, H2O, H2S, H2Se, H2Te. Like this, molecules are going to be formed. So, what type of hydrides are going to be formed? H2E type. Now, what is this E here? E can be, it can be oxygen, sulfur, selenium, tellurium. Okay, hydride of oxygen. Water molecule, if you take, it is the hydride of oxygen. So, four types of hydrides can be formed here: H2O, H2S, H2Se, H2Te. Further, coming to the different properties in this. This was first property. In this, let us see regarding the acidic character of hydrides. Acidic character. Acidic character of hydrides. These all hydrides, sulfur hydride, oxygen hydride, selenium hydride, tellurium hydride, how these are going to be showing the acidic nature. So H2O is less acidic than H2S, then H2Se, then H2Te, and so on. Okay, so this is the order. Why? What is the reason? What is the reason for the increasing acidic nature as we come down? Here, the reason is bond dissociation. Whatever energy is there, it is decreasing. Bond dissociation energy decreases. Bond dissociation energy decreases. See, as we come down the group, atomic size becomes large. Oxygen is small, sulfur is little large, selenium still large, tellurium still large. So, as the whatever the atomic size increases, whatever the bond length is there, it will increase. When bond length increases, to break that bond, less energy you need to supply. Less energy you need to supply. So, bond dissociation energy is decreasing them. To break the bond, you require less energy. So after that, what happens? So To remove the electron, it becomes easy. Ionization energy is less. When ionization energy is less, definitely it can get ionized, and there the acidic nature is going to increase. Okay, acidic nature. Similarly, second point in this, thermal stability. Thermal stability. Okay, so when you increase the heat, whether it is thermally stable, in what form it is stable. So here also the order is the same. Okay, the order is reverse. Okay, H2O is more stable, means acidic. You are able to break the bond easily down the road. So definitely thermally stable means water molecule is more stable than this hydrogen sulfide, then the hydrogen selenide, then the hydrogen telluride, and also hydrogen polonide. Okay, so this is going to be the thing. Now here also, what is the reason for the more stability, more strong stability of the water molecule is, again the reason is BDE decreases. Now what is BDE is bond dissociation energy. Bond dissociation energy or bond dissociation enthalpy. You can take it as enthalpy also. Both are one and the same. Bond dissociation enthalpy decreases. Since bond dissociation enthalpy decreases, so there the thermal stability is going to be stronger. Further, one more point. It is reducing property. Reducing property. Reducing property is getting reduced. When does it get reduced? When it accepts electron. Acidic character, we have said it is increasing. Definitely, reducing character, it shall be the other way, right? So, what is that other way? H2S less than H2Se less than H2Te. Here also, the reason is going to be the same. Down the group, when you come, atomic size is larger and larger. So when atomic size is larger, the bond length is large. Bond length is more. When bond length is more, bond can be broken easily. So when bond can be broken easily, its acidic nature is going to be more. That is one. Later, it is going to show the tendency to accept the electron stronger. So it will get reduced quickly when the bond can be broken there. So it is going to show the tendency to accept the electron more strongly. So H2O, if you take, it does not reduce. Exceptional case here, except for H2O. H2O does not show the reducing property. Okay, then next. Reactivity with oxygen, second point. Reactivity with oxygen. How does it react with the oxygen, and it forms what all types of the molecules? So all these elements, they form the oxides of the type. Oxides of the type EO2 and EO3. Oxides of the type EO2 and EO3. In this now, what are the E elements? E can be sulfur, selenium, tellurium. Okay, E can be sulfur, selenium, tellurium, and even polonium is also possible. EO2, EO3, dioxide, trioxides, it can be forming. In this, okay, dioxides and trioxides, they can be forming. In this, if you take O3 and SO2, O3 and SO2, these are going to be gases. O3 and SO2, these are gases. If you take the other ones, if you take SeO2, if you take SeO2, it becomes solid. So down the group as you are coming, when they are forming the oxides, so those oxides they can be solid in nature. Van der Waals forces will increase them. When Van der Waals forces increases, definitely there is a chance of the solid formation. Then in this again you have the trioxides. If you take the trioxides of the type SO3, SeO3, then TeO3. All the trioxides if you take, those trioxides are they are acidic in nature. They are acidic in nature. Generally, one thing remember, P block elements, whatever the oxides are there, they are generally acidic. In that only you have to again little bit look into what kind of acidity they show, whether it is increasing acidity, decreasing acidity. S block elements, they are the metallic elements. Okay, so metallic elements will react with oxygen to form the basic oxides. Metals will give basic oxides, non-metals will give acidic oxides. In that only you have to rank them again depending upon their nature. Further, reducing property in this. Reducing property. Getting reduced. So reducing property of the dioxides, if you take SO2 is strongly reduced than SeO2 than TeO2. All the dioxides if you take, sulfur dioxide is getting more reduced, is having more reducing property than the selenium dioxide, than the tellurium dioxide. Now what may be the reason here? It is due to because of inert pair effect. Inert pair effect. Down the group as you are coming, down the group, the inertness is going to decrease. So those electrons, they do not take part in the bonding, and that's how it's not going to be reducing in nature. Further, reactivity towards halogens. Third one, reactivity towards halogens. Reactivity towards halogens. Now here they form the halides of the type hexahalide, tetrahalides, dihalides. Okay, halides types. Halides types are EX6, EX4, and EX2. Okay, so hexahalides can be formed, tetrahalides can be formed, dihalides can be formed. In this stability, if you take again, stability between the fluoride, chloride, bromide, iodide, like this, the stability, if you compare, fluorides are going to be more stable than the chlorides, than the bromides, than the iodides. Okay, so whatever the oxygen family elements are there, whatever fluorides they form, oxygen fluoride, maybe hexafluoride, tetrafluoride, or difluoride, then that will be that fluoride will be more stable than the chloride, than the bromide, than the iodide. So these are going to be what? These are going to be, what is the reason? Bond length is increasing. As bond length in atomic size is increasing here, as you come down the group, from fluorine to iodine, in the iodine, the bond length is more. So with the Oxygen family element, when it is forming a bond, the bond length increases there. When the bond length increases, stability decreases. Here if you take fluorine, bond length is short. So because bond length is short, so that molecule will be a more stable molecule. That molecule shall be more stable. So bond length increases with increase in the size. Fluorides most stable, and among these, okay, chlorides are going to be more stable because of steric hindrance. Less steric hindrance is there. Further, in this only, if you compare the hexahalides, which hexahalide is more stable? So sulfur hexafluoride, selenium hexafluoride, then tellurium hexafluoride. Okay, you have got these. So now sulfur hexafluoride is more stable than the selenium hexafluoride, than the tellurium hexafluoride. This also is due to inert pair effect. Due to inert pair effect, it is so. Okay, right. And it is existing in what form? These all hexafluorides, these are existing in the octahedral form. These are the existing in octahedral. Octahedral form. What is that octahedral form? See, sulfur in the center, fluorine, 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 also fluorine. One is above, other is below. And these are going to be bonded like this. Now this we call it as octahedral. This is octahedral. Okay, 6 different atoms of fluorine are being bonded with the sulfur. Further, next. Tetrahalides is there. Tetrahalides, dihalides, monohalides. Let's. Everywhere reasoning questions you can be getting. Okay. All the reasoning questions you get ready there. Next, tetrahalides. Okay, tetrahalides SF4, SEF4, TEF4. SEF4, SEF4, and TEF4. These 3 tetrahalides can be formed, and as usual, as the atomic size is increasing, so shall be the van der Waals force will increase. So this will be a gas, this is a liquid, and down the road when you come tellurium fluoride, it's a solid. Little metallic in nature, so there the van der Waals forces are going to be strong. Then the type of hybridization here, okay, it is sp3d hybridization. You can check. You have learned the chemical kinetics topic. That hybridization formula. Using that hybridization formula, you can apply to this. You can check there what is the kind of hybridization. You will find that it is sp3d. Now, since it is sp3d, it shall be TPP structure, that is trigonal bipyramidal. Trigonal bipyramidal structure. Trigonal bipyramidal. So, sulfur in the center. So, you have one bond here, another. This is trigonal and bipyramidal. This is F, and F. You bond this, bond like this. Here you show lone pair of electrons. If you just join this, you join this. That becomes what? It becomes trigonal bipyramidal. Okay, so the lone pair of electrons are at the equatorial position. Okay, it is not on, it is equatorial. Suppose electrons were here or here, those will be the axial positions on the axis. It is not on the axis. Such a geometry, we call it as the seesaw geometry or trigonal bipyramidal structure we have said. Then coming to the dihalides. Dihalides. All these will form dihalides except the selenium. Okay, except the selenium. Except the selenium, all form dihalides. Except selenium, all form dihalides. Here the hybridization is what? Hybridization is sp3. Since the hybridization is sp3, the structure will be tetrahedral. Since the hybridization is sp3, the structure is going to be tetrahedral structure. Then next is monohalides. Monohalides. So in the monohalides, what is there? In the monohalides, what are there? S2F2. They exist in the dimeric form, we say. Then S2Cl2. Then S2Br2 and Se2Cl2. Se2Cl2. Okay. Then Se2Br2. All these are monohalides. Okay, don't feel sir, two atoms are there. So they are existing in the dimeric form. Two molecules are existing together. That's why we call it as the dimeric form. Okay, so these are monohalides. They exist in dimeric form. Like oxygen exists in O2 form, like that. Okay, exist in dimeric form. Monohalides of oxygen family elements. Monohalides of oxygen family elements exist in the dimeric form. So these dimeric, they undergo disproportionation. They undergo disproportionation in the reaction. Disproportionation means from one oxidation state, it is moving on to the two or more oxidation state. One example, 2Se2Cl will give what? It will give you selenium tetrachloride, SeCl4. Okay, SeCl4 plus Bs. Now here oxidation state of selenium is 0. Here it is -2. So it shall be +1 here. Each selenium is +1 to balance the fluorine, and here it shall be -4. Okay, to balance this -4, this shall be +4. So from +1 it is going to +4, from +1 it is going to 0. It is getting oxidized also, reduced also. For that reason we call it as the disproportionation. Further, preparation of oxygen. Chemical properties are over. Preparation of oxygen, and that oxygen, it is called as the dioxygen. NCRT, it has got its own terminology. So in the case of nitrogen, N2 molecule, they call it as dinitrogen. Do use those words only in the examination when we are writing the answers. And here oxygen we are going to learn, even that oxygen, it is dinitrogen. Okay, the next dioxygen methods of preparation. preparation. Okay, dioxygen methods of preparation. One method is from the chlorates. Okay, if you take potassium chlorate, 2 KClO3, 2 KClO3, this on heating, 2 KClO3 on heating in presence of MnO2. MnO2. Okay, so what you will be getting there? You are going to get potassium chloride, 2 KCl plus the other is it is 3O2. 2 KCl plus 3O2. So chlorates, nitrates, permanganates also will give the oxygen. So this is one method of preparation of oxygen. Other method is thermal decomposition of metal oxide. Thermal decomposition. Thermal decomposition of metal oxides. Thermal decomposition of metal oxides. If you take silver oxide, 2Ag2O. So this on heating, because its free energy will be very less there. So it's going to give 4 silver plus it is 4. Oxygen is obtained. Further, 2HgO. 2HgO also on heating gives 2Hg plus O2. 2Hg plus O2 it is. Not minus sign, I don't think it is minus sign here. Further, Pb3O4. 2Pb3O4. This also on heating undergoes decomposition to give 6Pb plus 4O2. 6Pb plus 4O2. Then 2PbO2 you take. 2PbO2. This also on decomposition gives lead oxide 2PbO plus O2. 2PbO plus O2. So everywhere, all these you are getting the oxygen. These are the laboratory methods you can take. Third method, decomposition of H2O2. Decomposition of H2O2, hydrogen peroxide, what they use in the nursing stations at the medical centers. Okay, so that H2O2, so on decomposition in the presence of metal or manganese oxide, in the presence of metal or manganese dioxide. So it shall give you what? H2O. H2O plus O2. What to balance here? 2H2O plus O2. Okay, this is a good method. Now coming to the large scale manufacture. How do you manufacture? So manufacturing, of course, it will be by electrolysis process. By electrolysis of water. On large scale, manufacture from water or air. From water or air, they are manufacturing oxygen. Air is going to refraction. So air is containing 78% nitrogen, 21% oxygen, 1% remaining gases. So if you go on cooling the air, nitrogen gets separated, air gases get separated, you are left with the oxygen. That is one method. Another method is water intake and electrolysis. So here, electrolysis of water. Electrolysis of water if you do. Okay. So what shall be obtained where? Hydrogen shall be obtained at the cathode. Hydrogen will be obtained at the cathode and oxygen shall be obtained at the anode. So at the anode there is oxidation, at the cathode there is reduction. So industrial method. Okay. From A, this electrolysis only, the other way let us see. So H2SO4, if you take H2SO4, it shall get ionized as 2H plus and SO4 minus. 2H plus and SO4 minus 2. So this is ionization of sulfuric acid. Later, at the cathode, what happens? At the cathode, two H plus ions will be there. Those two H plus ions take up the electron. It is reduction. It will form hydrogen gas. And there will be OH ions also produced during this. Those OH ions at the anode, okay, OH ions at the anode, they shall give you, how many OH ions will be taking? You will be taking two OH ions. It will give you H2O plus half O2 plus 2 electrons basically. Those 2 electrons only are used up here and you are obtaining oxygen at the anode. So this, when you, a little drop of sulfuric acid is dropped in a large quantity of water, a little drop of sulfuric acid in large quantity of water and carry on electrolysis. So H plus ions will get converted to hydrogen gas and that will be liberated at the cathode. In anode, if you take, at the anode, OH ions will be there. Those OH ions are going to be released. Those will get converted to water, oxygen, and they will release also 2 electrons. So important, what is our need here is oxygen. Further, for the air refractionation, I am telling you from air how it is being reduced. From air. So from air how it is being produces? First is removal of carbon dioxide and water. There are different techniques to remove the carbon dioxide and water. Air will be subjected to chemical treatment, so where you are going to remove carbon dioxide and water. Carbon dioxide and water shall be removed. Then liquefied and fractional distillation to give dinitrogen and dioxide. So then it will be liquefied. Whatever the remaining gas is there, it will be liquefied. After liquefying, fractionation is there. Fractional distillation they call. Fractionation also you can call fractional distillation. Fractional distillation to give what? Fractional distillation to give dinitrogen, N2 as well oxygen. Our need is the oxygen, 21% oxygen that we obtain. Further, next, let us see 4 or 5 properties of dioxygen and then I think we can stop for today. Lot of things is there. Still we have to learn regarding halogen family. And in this only still there is ozone, sulfuric acid, all that is there. That also we have to be learning. Then we go for 18 elements. Okay, properties of dioxide. Properties of dioxygen. And the properties of dioxygen is what? First one, colorless and odorless gases. It is colorless and odorless gas. First property. Okay. After this, next, solubility in water is how much? Solubility in water, 3.08 centimeter cube in 100 centimeter cube of water. Solubility in water. So this solubility in water, in whatever the value I am going to give, 3.08 centimeter cube in 100 centimeter cube of water. At temperature you have 298 Kelvin. At 298 Kelvin, it shall be that much soluble. Then liquefying point, it may be in the solid form. Oxygen may be in the solid form. So liquefying point and freezing point. Liquefying point. From solid, if you are changing into the liquid form. So that liquefying point is 90 Kelvin. In terms of degree centigrade, it shall be minus 182.96. Minus 182.96. You may check, you may correct me later if at all I am wrong. Okay, 182.96. You would have freezing point. Freezing point. Freezing point of this, it's going to be 55 Kelvin. 55 Kelvin. And that in degree Celsius, minus 218.79. Minus 218.79 degree Celsius. Then this is existing in three different stable forms. Isotopes if you take. Dioxygen, it is existing in three different forms. Three isotopes are there. So one is oxygen 16, another is oxygen 17, another is oxygen 18. 18 it is. 18. Okay, three different forms it is existing. Fifth one. It is paramagnetic even though it has even number of electrons. O2 if you take is paramagnetic. Why that paramagnetic arises is there are two unpaired electrons. Okay, reason because of two unpaired electrons in the anti-bonding level. Because of two unpaired electrons, it is going to be paramagnetic in nature. Last, okay, it is reacting with the metals except gold, platinum and other noble gases, and those reactions are going to be exothermic in nature. These are helping in the sustaining of the reaction, continuity of the reaction. So various oxides are going to be formed. So what are those oxides? 6th point. Oxygen O2 reaction with metal. O2 reactions. So it reacts with the calcium. It reacts with the calcium to form calcium oxide. Basic oxide. Metallic oxides are basic. It reacts with the aluminium. It reacts with the aluminium to form Al2O3. So 2Al2O3, this will be 3O2. Okay, those metallic oxides will be basic oxides. It reacts with the phosphorus. It forms what? E2O5. Phosphorus pentaoxide is being formed. It reacts with the carbon. To form carbon dioxide. Okay, so these two are metallic oxides, these two are non-metallic oxides. Further, it reacts with the zinc sulfide. ZNS, zinc sulfide, it reacts with the zinc sulfide. Oxygen reacts with zinc sulfide to give ZnO, zinc oxide plus SO2. To balance it, you have 2 ZnS, 2 ZnO, 2 SO2. 3 to the 6, 2, 3, 4. Yes, balance it. Further, it reacts with the methane to give carbon dioxide and water. CO2 plus H2O. To balance it, this is 2H2O, this will be 2O. Okay. This oxygen also can be reacted in presence of the catalyst. Reaction in presence of catalyst. Reaction in presence of catalyst. So what will happen when some catalyst is present there? Sulfur dioxide reacts with oxygen, 2SO2 plus O2 in presence of vanadium pentoxide to give 2SO3. This is a very important reaction in the sulfuric acid manufacture. Okay, this sulfur dioxide itself, it shall be absorbed in the water to form oleum, then it will be diluted to get the sulfuric acid. Very, very essential reaction in the sulfuric acid manufacture. Then 4Cl, 4HCl plus 4, 4HCl plus 4. Okay, in presence of what? In presence of copper chloride, CuCl4, CuCl2, I'm sorry, CuCl2. So there it gives chlorine gas, 2Cl2 plus H2O. 2Cl2 plus H2O. How many H2O? It is 2H2O. So chlorine gas also can be produced using this oxygen. Oxygen, when it is treated with hydrochloric acid, you are getting the chlorine gas. Next, uses. Last, okay, we'll take the uses and just finish. For the sustenance of life, continuity of the life, you require oxygen. For the sustenance of life. Then combustion process. All the combustion process, you require oxygen. For all the combustion process. Then in the welding, which kind of welding? Oxyacetylene welding. In the oxyacetylene welding, you require oxygen. Oxyacetylene welding. Further, for the manufacture of metal, okay, manufacture of metals, you require oxygen. Manufacture of metals. Later, okay, there are other uses also. Combustion of fuel is there. Oxygen cylinders in hospitals you require. In hospitals, where you require oxygen cylinder. Then another is all the combustion of fuels. Combustion already I have told. So combustion of fuels. So for the fuel to get burned, you require definitely the oxygen. And provide whatever the rocket launching, all that is there also you require this oxygen as a supporter of combustion. So this is what today what we have done. We have seen from the chemical the characteristics of the oxygen family elements, the chemical properties, the different hydrides, halides or oxides, all that. Later, the dioxygen methods of preparation, properties and the uses. This much we have done. In the tomorrow's class, let us move further. Okay. So do learn and just keep learning. You have got nice time to learn there. So after the 4 hours of the discussion, later in the evening, just have a look of all these 4 subjects. Okay. Thank you.